Section 310 is called the related rate section, and whenever you hear the word rate, that means with respect to time. So you're dividing by how much time it takes you to do something when you're thinking of a rate. So for example, the rate of speed might be miles per hour, distance divided by time. The growth rate of a population might be people per year. The number of people over the time units in that case are years. Or meters per second, that's distance over time again. Gallons per hour, that's a rate of water flow. So whenever you hear the word rate, it means that you're looking at over a period of time to see how much it changes. And in calculus, you can figure out related rates by taking derivatives, because derivatives tell us how things change with respect to each other. We can take the derivative implicitly, because a lot of the times the letters we're taking derivatives of aren't t. They don't stand for time. So when we take derivatives, we take them implicitly with respect to time. Any related rate problem, you need to take the derivative with respect to time. And when you solve these, there's a list of steps that you can go through to help you get the right answer. The first one is carefully read the problem. That one is really important. And the trick here is to identify what rates you're given and the rate you're trying to find. And how do you know what a rate is? Well, rates usually can be found by the units. When you look at the units of these numbers they give you, if the units are a fraction with time on the bottom, like meters per second, miles per hour, feet per second, those kind of things have to do with derivatives or rates of change. So that's usually how you can identify them. Also, sometimes they use the word rate. The second thing to do is find one or more equations that relate the identified variables. Usually it's one or two at the most. And a lot of times it has to do with the volume or the circumference. They're usually basic formulas we're using. Pythagorean theorem also. 3 is, after you get your equation, don't plug stuff in. That's what people love to do. They love to get their equation and plug stuff in, and that's not what you do here. After you get your equation, you take the derivative with respect to t. You have to get your rates in there. And the way to do it is take the derivative with respect to t. Always. And then you put your known values in and solve for what you don't know. And don't forget your units. And you can figure out the units by looking at what your answer says. The units on the top will be the top units. The time units will go on the bottom. So here's an example of a related rate. The edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? The problem with this is they're intimidating. But first, read the problem. We got a cube that's getting bigger at 2 centimeters per second. Each edge is growing at that fast. It's like a cubic balloon, maybe. And they want to know how fast the volume changes, and then they tell us how big the edges are when they do that. So we need to figure out the rate. And the rate here can be found by the units. Centimeters per second. That's a rate that has to do with the change in distance over time. And what does that rate tell me? The edges of the cube increase at a rate. Also, this rate has to be the edges of the cube. Now, if you'll notice the cube I've drawn here, I called the edges x. So if that's the edges of the cube and it's the rate that they change, the cube is on top, so the edge of the cube is on top, so that's dx, that's the change in the edge of the cube. And the time units, dt, is on the bottom. That's 2 centimeters per second. And I'll show you where that comes in a moment. But that's our rate. These are just centimeters. That's not a rate. That's actually a length. That's a distance. So now I need to come up with an equation that relates the volume to the edges of a cube. And I want to know how it changes. So the rate that I'm looking for is the change in volume. And what am I changing it with respect to? It's always time in these rate problems. So here's the volume of a cube. And if I call each edge x, then it's x cubed. There's my equation. A lot of times people will try to plug in now, but that's not the next thing to do. The next thing to do is to take the derivative with respect to t. The derivative of v is 1 dv over dt, because that's not the letter t. The derivative of x cubed is 3x squared, but since x is not the letter t, I have dx dt. And that's the dx dt we found over here when we identified that 2 centimeters per second. Notice it's positive because it's getting bigger. Well, we want to know how fast the volume is changing, so this is what we want to solve for. The change in volume over time. That's the rate the volume changes. The dx over dt is the change in side length with respect to time, and that's the 2 here. So to get our answer, we get dv over dt is 3 times, well, what did x represent? x represented the length of the sides of the square. And at the end it says the length of each edge is 50 centimeters. So I'm going to put in 50 for x because that's the length at that point. And dx dt is the number positive 2. So I work this out to calculate what I get. I got 50 squared times 3 times 2. And that gives me 15,000. Now I got to write down units. What will the units be? Well, notice the top is volume. Centimeters is the edges, so the volume is centimeters cubed. And on the bottom is the time. Notice the times are measured in seconds here. So it's 15,000 centimeters cubed per second. Notice how I got those units. V, volume, is on top, and volume units are centimeters cubed, because centimeters are my distance. T is on the bottom, and our T is seconds in this case. So that's a related rate problem. We get an equation that relates the variables, take the derivative with respect to t, and plug in. And here's another similar one. It talks about a spherical balloon. It's inflated and its volume increases at a rate of 15 inches cubed per minute. What is the rate of change of the radius when the radius is 10 inches? This one says the word rate. How nice of them. And you can also tell by the units, inches cubed per minute. And so it's talking about the volume and the radius. And it's a sphere. So we need an equation that relates the volume and the radius of a sphere. And that one you may not know by heart, but it's 4/3 pi r cubed. Now notice my 15 inches cubed per minute. The units tell me which one these are. The inches cubed tells me it's volumes on top. The minute is time. So this right here is dV over dt. The volume units, inches cubed, is on top. The time units, minutes, are on the bottom. And since it's increasing, it's positive. But I don't plug anything in. I take the derivative with respect to time after I find my equation. The derivative of v is 1, dv dt. 4/3 pi is a constant. The derivative of r cubed is 3r squared. dr dt. Remember, these are not the letter t that we're taking the derivative of, so we have to do it implicitly. Well, if you'll notice, these 3's will cancel, and I get dv over dt is 4 pi r squared dr dt. And now I can plug in my notes. Now notice, I know the change in volume with respect to time, and the units told me that. So instead of dV, I can write 15, because inches cubed per minute are volume units. 4 pi. My r is the radius, and at the moment that I'm looking, it says the radius is 10 inches. So I put in 2 for r. The change in r with respect to time, that's what I'm trying to find. That's the variable in this equation, dr dt. What is the rate of change of the radius? So I get 15 equals 16 pi dr dt. 2 squared is 4. So I divide by 16 pi, and I get 15 over 16 pi equals dr dt. I am not done. I still need to find units. My radius units are on top. That's inches. My time units on the bottom are minutes. 15 over 16 pi inches per minute. So notice it's pretty straightforward after you find the equation. Alright, we'll try it again. This one's a little trickier. It talks about a piston in a cylindrical container, and it tells me the radius of the container. It says it starts moving into the chamber at a constant speed of 3 centimeters per second. What is the rate of change of the volume when the piston is 2 centimeters from the base? So if you read this problem, you'll notice the rate, and it has to do with the piston moving into the chamber at a speed of 3 centimeters per second. And so what I need to know is an equation that relates the volume of the cylinder to the radius of the cylinder and the height, because that's where it's moving into the chamber. Now for a lot of equations like this, I may give you the equation on the test, because most people don't know the volume formula for a cylinder. But the volume for a cylinder is pi r squared h. Pi r squared is a circle, and then you pull it up into a cylinder, and that gives you that's when you're multiplying by h. But notice that this is different, because when I take the derivative here, I have an r and an h, which are two entirely different letters. So if I take the derivative, I need to use the product rule on the right-hand side. You can get around the product rule. If you recognize that the radius of this piston is constant the whole time. Notice wherever I go up here, I'm going to have the same radius. Wherever I go, I'll have the exact same radius on this thing. Whether it's here, or here, or here, the radius of a cylinder is constant. So it'll never change no matter where I am. So I could treat r squared as a constant and just take the derivative with respect to t. So here's one way to do it. For some folks, this is the way that makes sense. Pi and r squared are both constants because it doesn't change the whole time. The derivative of h is dh dt. That's one way to do it. The other way to do it is to use the product rule. For the product rule, u would be r squared and v would be h. The derivative of u is 2r dr dt, because I have to take the derivative implicitly. The derivative of v is dh dt. So by the product rule, if I'd have used the product rule, I'd have gotten v equals pi, which is a constant. U times v squared is r squared dh dt, plus v times u prime is 2rh dr dt. But if you look here, dr dt is going to be 0 because the radius doesn't change as this thing empties. So you may have, if you use the product rule, it would be at this point right here that you'd have to recognize that the radius doesn't change. And I would get pi times r squared dh dt, which is just what I got before. This is dv over dt. So you could have done it with the product rule, but even if you use the product rule, you have to recognize that dr dt is 0. The radius doesn't change. If you look at a can, the radius inside that can is the same as you drink it, all the way down. So in either case, I get dv over dt is pi r squared dh dt. And we can look at what we know. It says it starts moving into the chamber at a constant speed of 3 centimeters per second. Well, if we look at the cylinder, as this thing moves in, the volume is getting smaller. It's compressing it. So as this moves, when this starts moving in, the height is actually shrinking on this thing. So it's going to have to be a -3 when I plug that in, but that has to do with the dh dt. It's telling me the height, the change in the height of the cylinder. And it's getting smaller at 3 centimeters per second because it's squishing it. So I'm going to plug in for dh dt, I'm going to plug in -3. The radius of this thing, well, it tells me that the radius is 5 centimeters. So I can put in 5 for the radius. And now I can find dv over dt. 25 times -3 is -75 pi. Volume units on top, those are centimeters cubed. And time units on the bottom, those are seconds. So the trick to this problem is noticing that dr dt is 0. The radius is constant as you move down the cylinder. Here's one that uses the Pythagorean theorem. It talks about a 13-foot ladder leaning against a vertical wall. When the foot of the ladder is pulled away from the wall at a rate of ½ a foot per second, how fast is the top of the ladder moving down when the foot of the ladder is 5 feet from the wall? Before I start this, let me mention, notice dv over dt is negative. That means the volume is decreasing as time goes on. And that makes sense, because this is shrinking the volume of fluid as the piston pushes on it. So in this ladder, we're pulling a ladder out from the wall. So someone grabs the bottom of the ladder and pulls it out from the wall. And we want to know how fast the top is moving down. The trick to this problem is to notice it's a right triangle. And if I call these sides x, y, and r, I can think of the Pythagorean theorem that says that a squared, which is x squared, plus b squared, which is y squared, equals c squared, which is r squared. So I just used the Pythagorean theorem directly. So when I take the derivative with respect to time. The derivative of x squared is 2x dx dt, because that's not the letter t. The derivative of y squared is 2y dy dt. The derivative of r squared is 2r dr dt. And now we can go and look at what we have. Notice I got an equation, Pythagorean theorem, because I could see the triangle. I take the derivative with respect to t, and I go to plug in. Well, there's something I want to mention about dr dt here. R is the length of the ladder. So dr over dt is how the length of the ladder changes as time goes on. So imagine you go to the store and buy a 13-foot ladder and put it against the house. And then you reach down and pull the bottom of the ladder away from the house. And you can see it kind of fall down, right? As you pull that ladder away from the house, the bottom of the ladder, does the length of that 13-foot ladder change as it falls to the ground? No. The length of a 13-foot ladder stays 13 foot unless you bought a bad ladder. Otherwise, the ladder's broken and it's changing its length when the ladder stays 13 feet the whole time. When it falls to the ground, it's still a 13-foot ladder. The length of that ladder didn't change. So this dr dt is going to be 0 because the ladder stays 13 feet the whole time it falls to the ground. Dr is the change in length of the ladder, or with respect to time, and that ladder stays 13 feet. And 2r times 0 is 0. Well, then we have to see what we need. Well, we know that the bottom is being pulled away at half a foot. Notice the length between the wall and the ladder, which is what x measures, is getting bigger when I pull that away. So that's dx dt, feet per second, tell me that it's a rate. And it's actually the rate that x changes over time. So my dx dt is 0.5. Well, how far away is it? What is x going to be? Well, x is how far the bottom of the ladder is from the wall. And notice it says, how fast is the top moving down when the bottom is 5 feet from the wall? That's what x measures, how far it is from the wall. So I have 5 in for there, and I have I have 1/2 in for dx dt. So that means dy dt has to be the rate I'm looking for, but I have to figure out what y is to be able to find it. So what I'm going to do is I'm going to look at the specific situation that's happening right now. Right now I have a ladder, and in this ladder, or in this triangle, the bottom is 5 feet from the wall, and the ladder is 13 feet long. So I can figure out what y has to be with the Pythagorean theorem. 5 squared plus y squared is 13 squared. Y squared is 144, and you should check me here. So y is the square root of 144, which is 12. So I can put in 12 for y because I know what the ladder looks like at the moment that they're telling me at the end. So I take the derivative with respect to t, and then I plug in my knowns. And so now I can solve this. I get 5 plus 24 dy dt equals 0. I'll put a little line over here because that's side work. Yeah, 1/2 and 2 is 1 times 5, 24t. Subtract 5, 24 dy dt is negative 5. So I get that dy over dt is negative 5 over 24. Now I got to look for the units. Y units is the length from the ground, and that's measured in feet. T units is time, and that's measured in seconds. Notice it's negative, and that makes sense. Over time, the length from the top of the ladder to the ground gets smaller, so it should be negative. So the next one is a little bit trickier because it has to do with, or the next two, have to do with related rates that are conical sections that may or may not have constant, whose radius and height aren't constant. When you change the radius for the can, the radius didn't change. It stayed the same radius the whole time. When you have a cone, that's not true. The radius and the height can change at different rates, and neither can be constant. Here's one of them. It's sand falling from an overhead bin. Here's my overhead bin, knocking sand onto a pile that's in a cone shape. And the radius of the cone is always 3 times the height. Suppose the height of the pile increases at 2 centimeters per second. When the pile is 12 centimeters high, at what rate is sand leaving the bin? This is tricky on a couple levels. First, you got to figure out what you're trying to relate to each other. But in this case, they're talking about sand leaving a bin and falling into a cone. Well, if that sand is leaving a bin and falling into a cone, the thing that we're getting out of there is a volume, because that cone has a certain volume depending on how much sand is there. It's not an area because it's 3 dimensions. It's a whole big cone laying on the ground. So in this case, it's the volume of the cone that we're trying to relate. And the volume of a cone is 1/3 pi r squared h. That's not a formula I would expect you to memorize. And the problem is when I take the derivative, I would have to use the product rule because I have r's and h's. And if you'll notice, the radius changes as I go up the height of the pile. Notice it gets smaller as I get closer to the top. So now the radius isn't constant anymore. So I do need to use the product rule to figure it out. Except I was given some information to help me. It says the radius is always 3 times the height. I know for a fact that the radius is always 3 times the height. So the question is, which letter do I want to leave in there? The R or the H? Well, the next part of the problem is telling me how the height of the pile increases, and it tells me the rate. So that's dH over dt. It's telling me how the height changes with respect to time, and it increases, so it's positive too. So that tells me I want to leave the h's in there. So I'm going to replace the r's. Well, I can replace the r's by every place that I see an r, I can write 3h instead. And when I work this out, now I can get an equation that just has h's in it. I get 1/3 pi 9h cubed, which is 3 pi h cubed. So now I can take the derivative with respect to t. dv over dt is 9 pi h squared dh dt. We've decided before that dH dt is the 2 centimeters because it's how the height is changing. It tells me the pile is 12 centimeters high when I'm looking, so I can solve for the change in volume, which is how much sand is leaving the bin. 9 pi, the height of the pile when we're looking is 12, and the dH dt is 2. And so I calculate this, and I get dV over dt, which is the change in the bin. Let's see, I have 12 squared times 9 times 2. That gives me 2592 pi. Notice a lot of people will just leave pi in the answer. But that's around 7,800. 7,800 what? Well, the volume, if the height and radius are measured in centimeters, then the volume is going to be those units cubed. The time is seconds. So that's how fast the sand is leaving the bin, because it's falling onto the pile at that rate. Well, here's another one that's similar, except this one's the tougher one. It's the inverted conical water tank of height 12 feet. Inverted conical is kind of like the cups you use at the water bottles. And what happens is there's a hole in the bottom, and this stuff is draining out of here. And it says the height of this thing is 12 feet. And the radius, and that's the radius on the top here, is 6 feet. It says it's drained at the bottom at a rate of 2 feet cubed per second. Feet cubed per second. That's volume units on top and seconds units on the bottom. So that has to be the change in volume over time. And it says, what is the rate of change of the water depth? And the water depth here is going to be measured as the height h, because that's how deep it is. It's however tall this bit of water is. So I'm going to use h to represent water depth, and the volume of a cone, just like before, is 1/3 pi r squared h. It's the exact same formula we used in the last problem. And in the last problem, they said that the radius was always 3 times the height. That's not true here. Notice the radius changes as I move up the side of this thing. It's bigger towards the top. It's smaller towards the bottom. So if I take the derivative right now, I have to use the product rule. You know, the dr dt and the dh dt. U is r squared, v is h. A lot of work. But I can use similar triangles on this problem. If you'll notice, there's a big triangle that the whole thing encompasses. And that triangle is 12 feet tall and 6 feet across, because that's the radius. And there's also the little triangle that a generic height would build. And that triangle would have height h and radius r. Notice the radius changes as the height changes. But these are similar triangles, so that means that their ratios are equal. So that means h over 12 equals r over 6. That's what the similar triangles do, is they allow you to solve for one variable in terms of the other. And this is definitely a similar triangle problem. On a test, it would have a big old hint. Hint, use similar triangles. Well, I wonder, do I want to keep the r around or do I want to keep the h around? And I look and see what they tell me about. Well, they tell me how fast the volume changes. That doesn't tell me which one. The next question says, what is the rate of change of the water depth? And this makes me think, oh, depth of the water. The radius doesn't tell me the depth of the water. The height tells me how deep that water is. So I'd like to keep the h's in there. So that means I need to solve it for r. So I can erase all the r's and put h's in there instead. So I get 6 over 12h equals r, and 1/2 h equals r. And so I can replace r in the original formula with 1/2 h. This is what I did last time, except last time they told it to me outright. This time I had to use similar triangles. This is my side work, using similar triangles. So, I get the volume is 1/3 pi times h cubed over 4, which is pi 1/12 pi h cubed. I was thinking about the best way to write that. Now I have a function for volume that only uses the height, which will tell me about the water depth. Now that I have this, I take the derivative with respect to t. 3 times 1/12 is 1/4 pi h squared dh dt. dh dt is what I want to find because it's the change of water depth. So this is what I'm looking for. That means I can plug in for everything else. dv dt, well, it tells me that the volume of water, it's being drained. Since it's being drained, the volume is getting smaller. So this rate is -2 feet cubed per second because it's being drained. It's shrinking. 1/4 pi. In this case, my height that tells me, let's see, what would the height be? Well, the water depth is 3 feet. So if the water depth is 3 feet, that's what the height would be. Because the height is how deep from the ground, or from the bottom, the water is. So I can replace my h with 3 for 3 feet. And I can solve this for dh dt. I get -2 equals 9 over 4 pi dh dt. So I get -8 equals 9 pi dh dt. And -8 over 9 pi dh dt. It's negative because the height is getting smaller. It's draining. The units, it's feet units for the height, and the time units are seconds. So notice that this was a lot tougher because I needed to use a similar triangle to figure out how r and h are related. Similar. Whereas in the problem before, they gave me the relationship between r and h. So remember the basic steps with these, and I think it'll help a lot with these related rates. Figure out what equation you need to use, take the derivative with respect to t, and then plug in.